Today I want to present you some periglacial processes and landforms, and these are things that I think, if people are interested, could be modeled in the lab and numerically. And for that, I want to say, in my lab, I welcome maybe 5 to 10 interns a year. So we offer funding to come to the lab and do some modeling. Tomorrow I'll present the facilities we have, and we usually have 3 to 4 invited profs that also do physical modeling in the lab. So if somebody wants to do a sabbatical in Montreal, call me. Okay, we talked about it a little bit yesterday, frost cracking. We use also the term gélie fraction, that comes from the French. And we have various modes of frost cracking, but it's kind of blurry in the permafrost literature how it works really. So usually it will be presented in relation to ice formation. So we have cryosuction, or we have ice in fissures and fractures, and it will propagate, and then you will crack your rock like that. You can also have cryosuction even in rock, and you can create ice lenses, and the formation of the ice will exert pressure, and you can create that kind of material. And here you have a permafrost core. This is sandstone, so this is bedrock. This is sedimentary rock, but sandstone do have a porosity. And water can migrate through that porosity, and what you're seeing here are ice lenses that broke the sandstone. So that's another process to break rocks. What it creates in terms of landforms is block fields, also called Felsenmeer. So here you have a limestone. It's not a deposit, it's really frost cracking. So imagine a large slab of limestone, and it's subjected to cold climate, and it will break like that. So one process that will be very interesting to do in the lab, and it's not necessarily complicated, is the coefficient of thermal contraction and expansion of rock. So in this place, it's Igloolik in Nunavut, so northern Canada, Arctic. You go there in the winter, there's no snow there. There's almost no water. Yet you have all this limestone that is shattered, that is cracked. So limestone is a fine-grained rock, sedimentary rock, that can be altered just by water. So it will create karst, as you have in France, for instance. But another process, and there was only 1 or 2 researchers working on that, is the expansion and contraction of the rock with no water, or almost no water, unsaturated. So this thing also can crack the rock, but you will very rarely see that in the literature. And it's because also it's not necessarily well measured. So what you need in the lab to do that is high resolution laser, for instance, and a slab of rock that you know the dimensions, the 3 dimensions, and then you subject it in a cold room to cold temperature, and you decrease the temperature, and you measure how it contracts as it goes down in temperature and how it expands like that. So in France, in Caen, there was a lab who worked several decades on frost cracking, but it was always with water. So that will be something that is feasible. And if you look, the coefficient of thermal contraction and expansion is super well known for building materials like steel or copper and things like that, but for natural material, not really. What we find in the literature, if you go back to the original paper, it's always blurry how it was measured and so on. So that will be something very interesting to do in a cold room. And you see here the coefficient is pretty low. Sandstone will react well, and granite will be in between. Granite is an igneous rock. It's not a sedimentary rock, so it's not porous like sedimentary rocks. And igneous rocks will have different minerals. So then we talk about the thermal expansion and expansion of the minerals inside. So they have different thermal conductivity, these minerals. So one is not doing anything while one is contracting, and this creates what we call in engineering fatigue. That comes from French, fatigue, of the material. And you see it very often on concrete, on asphalt pavement, and there's a lot of this contraction that comes, but with igneous rock, this is what we believe creates the frost cracking. So if you have a granite cliff, sandstone cliff, and limestone cliff, granite will be much more resistant than the other ones. Okay, so that brings me to a phenomena that is super interesting, and this one too, if somebody wants to come to my lab to model that, I'll be happy to receive you. So we call it sorted polygons and sorted circle. So I'll explain you a little bit what we have here. So imagine this place with nothing like that, it's just rock. We're on top of a mountain in the high Arctic. We see the Arctic oceans down there. So, and this island, very strange, was not glaciated during the last glacial maximum. Okay, it's just beside Ellesmere Island, but Ellesmere has big mountains. So the precipitation were falling on the mountains, creating glaciers, and when it was moving north, it was depleted of precipitation, so no glaciation there. If it was, and why I know that, because now we're getting back into the geomorphology and quaternary stuff. We have on the island, we find shells, seashells, so due to marine transgression. And when I first collected these shells, when I found that, I dated them with radiocarbon dating, and I have dates of 26,000 years old. 26 is straight in the peak of glaciation in North America. So in this area, we know if we have a sea, open sea that leaves some shells and so on, there was no glacier on the island. So if there was no glacier on the island, and I have several of these dates, because when I found that, I said, it's another lab mistake, so I sent it to another lab. Okay, I sent it to the original lab. The three have the same dates. I sent more. Always 23, 26, etc. So I know it's good. So it was not glaciated, which means that the rock there, before the formation of that, was exposed to cold climate for at least 100,000 years old. So what you're looking at is the evolution of a rock surface in periglacial climate that is cold, over 100,000 years old. Of course, in the lab, I don't think you will model something like that. So it takes time, definitely. You have the rock, and this one here is igneous rock. It's not a sedimentary rock. It's similar to a granite. And it's exposed to cold climate. It starts with what we've seen in the previous slide. It starts with cracking the rocks like that. Eventually, you have all your surface. As you can see, it creates block fields. We have that in the background like this. The whole mountain is cracking, if you want. But when you crack a rock, yes, you crack it in two, but you will also create a little bit of smaller diameter particles. And there's not a lot, definitely, but these particles, smaller, will be frost susceptible. Like Robert presented, there will be cryosuction in them. And you start to have what we call a sorting. So this little graph here is explaining that. At first, you have your surface like this, and you start to have formation of ice lenses. And that's a terrible graph. It's not mine. You will pardon me, Robert. We don't think we have ice lenses of this shape. But you have ice lenses forming, and you will push. It was also presented by Robert for agricultural field. You will push your rock towards the surface. So the ice form in the finer sediment can be sand, can be silt, and the ice lenses that are formed push the things upward. At first, you don't have a bulge like that. At first, it's pretty much horizontal. But eventually, you push that, you concentrate the fine material in the center, and your rock goes to the top. At thawing in the summer, the surface subsides, it goes down like that, and the rock that were brought to the top starts slowly moving towards the periphery. So this is what we see here. These rocks were moved to the periphery. And you can see also a sorting, with distance to the circle. And here you have the concentration of fines. And this is the center. This is a notebook. So you can see the expansion and the cracking that occurs like that. That's a proof of this thing here. It's also blurry in the literature. It's more numerical modeling and field observation, but people think it's like that. You have a fine domain, and then you have a coarser border, and then it's followed by a fine domain. So often you see it in fields like that. The one that I presented at the beginning of the course from Antarctica, that's the same. Was not glaciated. It's the dry valleys in the McMurdo, so they have time to develop these things. And the same process, so you have these sorted polygons or sorted circles. They occur on kind of flat to low sloping surfaces. If you arrive on slopes, then these cells, if you want, they elongate, and eventually they create what we call sorted stripes. So you have a line of coarse material and a center of finer material. So you have an example here. So that's the super high-tech tools of a geomorphologist. We do everything with that. So you have a center with finer material, and here you have a border. Now it's covered by moss. I'll explain why. And underneath you have coarser material. There's suddenly a very big interest for that in terms of climate change. If you look at the picture here, what you see in pink are small tundra flowers. They grow right in the coarse border here. That's totally counterintuitive. You want plants to grow, you put them in fine soil. And yet here in the Arctic, they follow the area where you have the coarse material. Well, on slopes, this coarse material, it's water flow. So the hydrologists, instead of sorted stripes, call that water tracks. And I met a French guy because I was trying to find a translation in French for water tracks. And then I met a guy random. He said, "Ouais, moi j'appellerais ça des sillons hydriques." I said, "Oh, interesting." So this is where life forms in the high Arctic. And for climate change, this is where, if you have life forms and plants, this is where you will have carbon. And there's a big focus, as you know, on carbon emissions from permafrost regions right now, because it creates a positive feedback, apparently, to warming. Not clear in reality. So here you see the exact model of this thing. You have the polygons and the circles, and then you have the stripes like that. And it affects super vast areas of the Arctic, this thing. No, here in the Arctic, that would be a few decimeters, maybe 60, 80, 90. And like I said yesterday, the active layer is not a fixed thing.
Yeah, it's just because if you have a wavelength, you wait that the process that governs the emergence of this wavelength is linked to another to length in the easier system.
Yeah.
I thought that from the previous schematics that it was the thickness of the active layer because of the holes.
Yeah. Well, here I show perfect examples. Just for understanding, but the size of the circles and things like that will vary quite a bit. And also what Robert shown and what I've shown from Antarctica, it's always the same picture. 4, 5, I swear, it's 4 or 5 of these circles, but I know the guy who took that. And you look beside it, there's no so beautiful circles. But yes, the wavelength will be interesting to analyze because here you see it's really regular. Yeah. Yes?
Do you have an estimate of the typical time scale for the formation of such landforms?
Yes and no. General idea, because I know that this place, this exact place, this is one of my field sites, the sea was gone at about 3,000 years ago. So that's the minimal age for that. Because when you have the sea, and I would say you need to upgrade permafrost, so maybe another 500 years to develop, and then you need to start the sorting. So it should be hundreds to thousands of years. But in the lab, the process of moving things, in a convective way could be done, by playing with freeze-thaw cycles. Like in the high Arctic, we don't have a lot of freeze-thaw cycles. It's just a little bit in the summer, then it's frozen, stays like that. In the lab, we can play with freeze-thaw cycles by let's say 10 minutes and see what it does in terms of convection or not. Okay. Now I want to talk about a different landform, and maybe there's things to do in the lab, but not necessarily easy. So it is ice wedge polygons. Why I want to present that? Because this is the most common permafrost landforms in the high Arctic, above the Arctic Circle. And it contains ice, I will show later, a big amount of ice. So this is, I won't explain how it forms, but the degradation of that is changing the landscape totally. So it is, again, frost cracking of the ground and not of the rock. So when we have cooling, so we freeze the active layer, but when we go down in temperature, it contracts like any solid. And when it warms up, not necessarily by thawing, just from -10 to -2, for instance, it expands. And this thermal contraction creates what we call frost cracks. This is an example in the field here. And it results in this pattern ground that we call ice wedge polygon. So I'll show you a little cartoon how it works. So you have a surface that is freezing its active layer, and it creates some contraction kind of cells, if you want. And this has been modeled, and it was not a computer, it was Art Lackenbrook, a physicist in the 70s. He really got the thing and the right equations, but he did not have proper values for materials, so some of the values don't make sense in terms of size and so on, but in terms of process, it was really good. So you have the contraction of the ground. Eventually, if in the Arctic, the ground cannot stand this contraction. It creates a lot of mechanical tension. To release the mechanical tension, you create a frost crack. And this frost crack will release tension on a given volume of soil. Then you have another volume of soil that requires its frost crack. Then you have it perpendicular as well. So you develop this network of open frost crack by thermal contraction. So here also that's a coefficient of thermal contraction expansion. Again, if it could be measured in the lab, that will be nice because we have very few values for natural material. So it's the change of length, width, and thickness. It's related to the coefficient of thermal contraction and expansion, the original length, and the temperature change. Here, the coefficient is to the -5, so it's an order of magnitude higher than for rocks. So for dry sands, this is what you have: frozen sand, ice-rich frozen ground, and pure ice. So you develop the network of crack, then you arrive to the summer period. So your snow will melt, and the frost cracks are still open, and water will trickle down the frost crack, very simple. As it gets into the crack, it refreezes almost instantly. So this is an example of an ice vein here in a frost crack. Then the active layer will thaw. So this ice vein in the active layer will melt, definitely, but the one that is in the permafrost will remain. So frost cracking goes from, in the Arctic, from 2 meters up to 4 meters deep. So then you have this ice vein that is 4 meters in the ground. This cycle will be repeated year after year. And cracking will occur in the ice, because if we look here at temperature that we find in the field, tensile strength of ice wedge, 1 megapascal at -22 megapascal, and the enclosing sediment, let's say it's silt, 1.5, 2 for sand. So it's easier to recrack in the ice. Next summer, the active layer thaws, the ice vein thaw, but it remains in the wedge that we see here, and it grows with time. So in the field, what we did, so you have an example here of polygons. We have a small data logger, and we make a very simple setup. We extend electrical cables across ice wedges or ice wedge junctions like that. So you have your ice wedge, you have usually a ridge there, and then we extend a cable across. And then when we lose electrical signal, we had the frost crack that broke the cable. So we know the temperature of cracking. So this is an example of broken cables. What we observe, the daily main temperature is -20 to -40. And what happens is it's kind of you need a very cold ground already. So there's a conditioning, a cold conditioning of the ground. And eventually you have a cold spell, so a drop of temperature. So it's just the atmospheric circulation. You have a cold spell, and when you have a drop in air temperature of about 8 degrees C, then it cracks. And then we measured the thermal gradient. You need about -11 thermal gradient in your active layer, and temperature at the top of permafrost there. So we know pretty much the conditions, how it works. But this is for a given material. Here it's a mix of fine-grained sediment and peat. Again, measuring the thermal contraction and expansion of material will help to do that. But in the lab, that's super complicated. I don't know any cold room that go to -40, for instance, that you can have a significant volume of soil. So that might be difficult to do the frost cracking, but maybe we can measure the parameters that lead to frost cracking. So in the field, what does an ice wedge look like? So you have the active layer, the zone that thaws and freezes every year, and the accumulation of ice veins create these ice wedges. Usually the polygons will be 15 to 20 meters in width. So you will find another guy like that 20, 15 meters away, and another one infinitely in the Arctic. So this is called the underground glaciation. So since the glaciation, we have formation of these ice wedge, and we're capturing water, transforming it to ice, and it's sealed there. So we had that for, let's say, 12,000 years. Now we're melting these ice wedges, we're thawing the permafrost, and you can imagine, of course, if you thaw, you melt this thing here, the subsidence that occur, the depression you create, the water that goes in it, the convection that goes with water, and then we go. So there's a positive feedback to permafrost degradation. And that will be very interesting. There's a guy from NASA who used remote sensing to identify all ice wedges on the planet. You know, sometimes we find people like that. I don't know how many millions of them he figured out. And it would be probably possible to evaluate the amount of water that is stuck underneath, now that we know the amount of ice wedges. And this thing will contribute also to sea level rise eventually. So that's an interesting pattern. And also, this is Michel Allard, that was my PhD supervisor. As you can see, he's very happy with his shovel. And you have here an active layer with peat and so on, but here you're in bedrock. So frost cracking can eventually also occur in rock. So you won't find that in books, and we have not published it yet, but we see it in several areas. It occurs in sedimentary rock. So it's also a mode of landscape evolution that is pretty strong. Okay, here, I want to show you something very special. We discussed about syngenetic permafrost, the rise of the surface, the top of the permafrost table that rises with that surface. So yesterday I presented that. In the case of permafrost with ice wedges, you add layers of material. Oh, the ice wedge goes up as well because the little ice vein cannot melt in the summer. You add material, it goes up. You add material, it goes up like that. This is in Alaska, and this is a deposit that is about 50,000 years old according to our radiocarbon date. What you're looking at here is an ice wedge. So this is a very performing student rappelling down because we sampled the ice wedge for ice analysis and oxygen isotopes and so on, that rappelled down the ice wedge to sample. Another one was here. This is the material in between the ice wedge. This is the polygon, if you want. And all that is about 70 to 80% ice per volume. This, of course, is 100% ice per volume. And so this is me calling the shot, as usual, doing nothing. Sample this, sample that. So you can see it's absolutely enormous. We were called there by Alaska Department of Transportation in this area. They wanted to develop a new road. And they wanted to know the permafrost conditions because road will affect the thermal regime. Usually it creates permafrost degradation. So in fact, we told them, we don't think you should put a road somewhere in this area. That was as simple as that. For us, it was really easy contract. Yeah.
So you say 70 to 80% of water even in the rock spot?
Yeah. Here, this is wind-blown silt. We call it loess. So small particles, 60 micron to 90 microns, deposited and at the surface, and then you have plants that grow. So it's organic matter. And this, when I said that syngenetic permafrost is super ice rich, that's it. It builds slowly and in the soil, and then you have these very high amount of ice there. And it's beside pure ice.
So it's almost a huge lake.
Yeah, so let's say we apply warming to that for many times, because you imagine the latent heat in this thing? Let me do an editorial comment. Maybe you heard about the Alfred Wegener Institute in Germany, working on permafrost deposit like that. So they calculate carbon stocks and nitrogen stocks and phosphorus stocks and virus stocks and all that. And they say, well, if it thaws, we're going to be in trouble. This will require probably, if it's not exposed, just atmospheric warming, more than 10,000 years to thaw. So we'll probably reach the next glaciation cycle. So we'll never see those buried viruses. By the way, they're not dangerous. It's just a scam to receive funding.
Well, this is an exposed cliff that was exposed by some other person. This is a cliff that was exposed. You didn't dig this.
No, this is by a river. So before, when we started to work in this area, we looked at exposures, which is much easier than coring. And we found an area with a recent sat image that the river was encroaching. So we went there to analyze that. Yeah. Yes?
A question. I'm quite interested in crystal. So in this sense, if you dig a big piece of ice, is there a high probability it's a single crystallize?
No. No. Yeah, polycrystalline ice. And let me go back a little bit. That's an ice vein. So you have the walls of your frost crack, water goes in, and then it freezes like this. So you have a seam of bubbles here, and you have ice on the side. So when you look at this ice wedge ice, it's vertically aligned like that. It's really easy to recognize in the field. Yeah. Okay, so we were there. Yes, let's say we thaw this whole thing. So we will have it if we have 80% ice pulp volume, the surface will be something like that. So it's an extreme that I'm showing you, but it's to show you the impact of, for instance, ice wedge formation, cryosuction, and ice layers development, how much ice we have, and the topographic changes that comes when we disrupt these things. So what we are seeing right now for Arctic region is really not a lot. So we see a lot of catastrophic stuff, but it's only surface stuff. We're going into major topographical changes. Then you affect the hydrology, the hydrogeology, then your ecosystems will follow, and then we don't know in which mess we're going. Absolutely not. So this kind of deposit, we find it in many places. Russia, Siberia, northern Canada, Alaska, we find that. These are areas that were not glaciated during the last glacial maximum. They were exposed to periglacial climate for 50, 60,000 years. And they developed these massive ice wedges and polygon center full of ice. Also, the big interest right now, it has the organic matter is carbon. You thaw that, and you'll find carbon all the way to the bottom. And just a quick note, if it's that wide here, it extends surely for like maybe 10 more meters before it goes to the tip. There's a lot of carbon in that. If it thaws and microbial activity starts in there, there will be quite a bit of greenhouse gas emission that will accelerate the current warming. So this is what it looks in 3D. So you have this network of wedges and so on. So you can almost consider these areas, it's almost ice only. It's really, really a lot of ice. Okay, so I want to discuss about another landform that is related to what Robert presented, cryosuction. Cryosuction is the process, and it creates ice, whoops, little mistake, ice segregation, and so accumulation of ice, and this accumulation of ice creates heaving of the surface, frost heaving. So the water that is at depth migrates towards a freezing front, and the freezing front eventually goes down in that water and create ice lenses. So this, and I'll go right there, creates these landforms. It's called palsa. It's from Finland term. So you have epigenetic permafrost, so it's different than the other one. You have a deposit, usually it's marine or near-shore deposit that goes there, and then the permafrost are grade in it. So at first, the freezing front goes fast. But as you go down with thermal diffusivity, the freezing front goes very slowly. It's almost stationary, and water can just migrate. So you're below the permafrost limit. So water migrates. So the difference with epigenetic permafrost, with syngenetic permafrost, is that this one gets richer as you go down. The ice lenses get thicker as you go down because of thermal diffusivity that make the freezing front kind of stable. So it will degrade differently than syngenetic permafrost, which is ice-rich all through the sedimentary column. And these ice lenses can be quite thick. So at depth in Palsa, okay, here you have trees that are like 15 to 20 meters tall. The Palsa is about that elevation here. So you created 20 meters of ice lenses. And in fact, you can have what we call massive segregated ice that makes 10 meters, an ice lens of 10 meters. And this forms in the subarctic. It's not in the continuous permafrost, is in the discontinuous permafrost zone. So you have permafrost, this will be no permafrost. Permafrost, no permafrost. So this is discontinuous. And this one is actively degrading everywhere. And when it degrades, it creates little ponds that deepens. Eventually, these ponds connect, and you develop a new hydrological network that goes with it. So you go from terrestrial to something that is more fluvial landscape. Also pretty interesting. And that could be modeled in the lab, the Palsa, in a quite simple manner, I think.
How is this different than a pingo?
Oh, a pingo. A pingo is different. A pingo, it's an Inuit term. And it's in Inuktitut, it means blister. Un petit bouton. And pingo is a closed system, is a closed system thallic that develop under a lake, for instance. And it's not uncommon in the Arctic that these lakes drain. So you have, just for instance, a breach in the margin of the lake, and the lake will drain. And all this water will also create convective heat transfer, and it will enlarge. Then you drain your lake, and you have a fully saturated sediment that is enclosed in permafrost. So you have inward freezing plus freezing top down, and usually lake bottoms will be with sand, and you create ice, but you expose water in front of the crystals, and you create some kind of a water lens. And eventually the freezing front get into the water lens, it expands, and you create this pingo like that. So these are the two ice core mounds that we find most often.
They look sort of broken on the top. Pingo.
Yes, because you need to accommodate the deformation. Eventually they crack. Same thing occurs with Palsa when you form them with cryosuction and so on. It creates cracks, and that leads to a natural cycle of degradation eventually for the pingos and for the Palsa. Okay. Another process I would like to discuss is soil creep. Some people call it, well, in North America we call it solifluction. In Europe and in France, solifluction is for non-permafrost areas. So French will use usually gelifluction. But in literature, you will find mostly solifluction. So what is solifluction is thawing of the active layer on a slope and the movement of material that goes with this thawing on the slope. So you need some kind of water source, not only the lenses in the active layer, and when it melt, this ice, it will create the water necessary for the movement to occur. So you have a thawed zone over a frozen zone, you have a shear horizon here, and then the movement will start moving down slope. And because it's muddy and stuff, you will move rocks also down slope like that. So it's very common processes on slopes in the high Arctic, subarctic, and you have it also in freeze-thaw areas, periglacial. So an example of that, you have here ice patch, which is snow that recrystallizes into ice over years. So you have also in the summer melting of this ice, water that is released, and then you have the sediment that starts moving down slope like that. So these lobes that we see are about 400 meters long. So you take some kind of material, and with this process, it's slowly moving down the slope over hundreds to thousands of years. And it's just move all the material that you can have, rocks and whatever you have. So an example here, you have your slope, you have your water source, and look at the number of solifluction lobes that form like that. And this is a view from the top of a solifluction lobe. And the material is moving with water, so usually more fine-grained sediment. And as you can see, this is where the plants will colonize because you have water. So that's also a focus of life formation in the Arctic. So as we warm the Arctic, we will see more and more of that vegetation appear, and eventually we're moving polar deserts toward the other biome, more to the south, Arctic tundra, slowly. That's a very efficient process. And a closer example of that, it's also interesting for permafrost dynamics. So as you move your material, you create some kind of syngenetic permafrost. You add material down slope. So here is a solifluction lobe, this is the water source, and you're moving material down slope, and it will create syngenetic permafrost aggradation at one point. But downslope, the water that is moving will create permafrost degradation. So there will be subsidence. And the stuff will be starting to move faster this way. So this is a study we conducted in the high Arctic. So it can be in the form of lobes, or it can be solifluction sheet flow. So just the old material that is flowing, and then you create your great permafrost. So even in the context of climate warming, or in a context of climate warming, these lobes will accelerate. And interestingly, they will create some permafrost in a context of permafrost degradation. So it's not linear, as you can see, the dynamics of permafrost. And here again, these are permafrost cores that we collected. And you can see from the lobe, so this area, so you can see the cryosuction and the formation of ice lenses. Black is ice. So this is the picture, this is the CT scan, and again, full of ice there. Okay, now that I've presented some of permafrost aggradation processes, we'll move to where we're going with the permafrost region, which is permafrost degradation due to climate change. So the Arctic, since 1971, warmed 4 times faster than the rest of the planet. So it's quite fast. And some high-impact papers were published in Nature recently that permafrost is degrading at the global scale. So we have all the boreholes equipped with thermistors. We analyze that at the circumpolar scale, and we see that everywhere since the 1980s, everything is warming. The thing is that it's true, but it doesn't change much, really. So if you're at minus 15 and you warm your permafrost at minus 13, what happened? Yet. It's just, you're going from frozen, cold frozen to cold frozen to cold to a little bit less cold. So until you arrive at -2 approximately, it doesn't change much. At -2, we start to have a lot of unfrozen water content in the permafrost. And then it changes a lot of the processes. You can have water migration in your sand, in your soil, etc. And look at the how flat it is when you arrive close to 0. So this is a problem with thermal monitoring. When we arrive close to 0, nothing changed in the temperature almost. We're extracting latent heat before phase change. So it appears, okay, this is cool, this is relaxed to the south of the permafrost region. It's not working, it's not warming a lot. No, but it's preparing itself to what we call the final thaw, so the phase change. So we need something else than temperature to evaluate permafrost degradation, and that's mechanical. And this is complicated. There's not a lot of, we can use INSAR satellite imagery to do that, but it's kind of complicated. Yeah, so what happens with this permafrost degradation? First, we warm the ground. Then we increase the active layer thickness. And this is all the catastrophic manifestation of a geomorphological manifestation that we see, because we arrive in the ice-rich zone that I presented yesterday, transient layer, intermediate layer, it's full of ice, but it's not for a big thickness. So you have a super strong reaction, but it will not last forever. Once you're done with this ice-rich layer, all the processes will start to relax a little bit. Eventually, and this is concerning, is the development of thallic. So at one point, you have supra-permafrost thallic. So you have a zone which is unfrozen. You have the active layer that freezes and thaws, and in between, you start to have a zone that never refreezes, and then you have the permafrost. When we have that, then we're good for permafrost degradation. So, and it's difficult. You need to go to the field, you need to core, probe, and see what it is. So we have started to see that a lot in Siberia and also in Northwest Canada. So the two main areas. For the rest, we're still having just a deepening of active layer. Eventually, when your thallic expand, you still have permafrost at depth, but it's relict permafrost. It's not in equilibrium with the temperature. You have relict permafrost, eventually final thaw. So relict permafrost can stay there for a long time. At about 100 meters in Poland, there is permafrost. It has been exposed to warm temperature for a while. And for instance, in Alaska, a place that was deglaciated 12,000 years ago, it's still degrading because you still have permafrost at depth. So it will take forever, and usually we will arrive to the next glacial cycle, so cold temperature, before complete degradation of permafrost in the Arctic zone. So this one stays there, and when we have a cold climate, then it reaggrades and it merges together. This is what we have in Canada and in Russia, for instance. And in ice wedge areas, you start to degrade these ice wedges, usually at the junction of ice wedge, which are a little bit higher in the landscape, and you start to develop thermokarst ponds that evolve eventually into lake and large lakes. So this area here, these lakes, it was all terrestrial surface a few thousand years ago, and then you're developing all these lakes. Lakes are focal point of greenhouse gas emissions, especially methane. So it's major ecological change for the system. You go from a terrestrial to a almost, the limnicity of this is pretty high. So you change completely your ecosystem. Large impact on the environment. Another mode of permafrost degradation here in Alaska along the Beaufort Sea coast is the abrasion or thermal erosion of coast. So this is convective heat transfer with seawater washing the base of the cliffs, and eventually you create some kind of a niche underneath, and the coast will just, the blocks will just collapse like that in the sea. So this thing occur in a matter of weeks if you want, but the aggradation of this permafrost could have taken maybe 2,000–3,000 years old. So the speed of degradation compared to aggradation is just enormous at the moment. So it's creating big changes along the coast. Another mode of permafrost degradation is what we call thermal erosion gullying. So I told you that snow meltwater will get into the frost crack and refreeze. Not always. If you have concentrated water flow, which is not abnormal in the tundra, and it goes into a frost crack, it can infiltrate, and convective heat transfer will melt this ice and create underground erosion. So here we have a student, very curious student, that went down in the hole, and you have a network of tunnels that develop. So again, you have a terrestrial surface, and then you create these big gullies. So every polygon is about 10 to 15 meters wide. And what you're observing is the development of a hydrological network where you were in terrestrial environment due to this thermal erosion process. So an example of these tunnels, so you have the person for scale there. So you have tunnels about that big. We could walk in them. It was just before collapse of the roof of the tunnels. And again, it took about 4,000 years to grade that permafrost, and this was created in 2 weeks. So totally different scale of evolution. So it's 1999 during the summer, and then 3 years later, we have these big gullies. So convective heat transfer with water is 1 to 2 orders of magnitude faster than atmospheric heating. So all the models right now, they're presenting permafrost evolution with conductive heat transfer. It's not coupled with convective so far. So what we're seeing, you know, the images like at 2100, if you take only one process of thawing, what does it mean, really? If you put only conductive heat transfer and then you tell me this is how it will look like at 2100. I have a little bit problem with that because it transfers into policy sometime. So the situation could be much more catastrophic than what we're seeing right now. And we have several types of mass movement that are formed with climate change. Rock falls and rock slide. So in 2003, there was the Zermatt in Switzerland. The top of Zermatt just collapsed. It was the ice that was holding the rock together. That was pretty interesting because we were in Switzerland for the International Permafrost Association conference. And then during the conference, Zermatt collapsed. And we said, wow, the Swiss, they're powerful. They must have organized that for the conference. Something like that. Yeah, so rock slides, and it's occurring big time now. You might have heard glacier collapse recently in Switzerland 2 years ago, I think. That was related, in fact, to the melting. The rocks, in fact, was ice melting. And then in sediment, we have what we call thaw slump. And this is also fairly common. You have a helicopter for scale. That's not a toy, that's a real one. So that's fairly big. Again, what is difficult to see where we're going is that when this material goes down the slope, if it arrives on terrestrial environment and you're in cold enough climate, you should have permafrost degradation. So we have permafrost degradation and permafrost aggradation at the same time. But many of these thaw slump, they exit in rivers or lake or ocean. In this case, there is no more permafrost degradation. and it's really, really affect the water quality of the system. For instance, this place in Alaska, we were called because there was a native village and they saw some gray water and the fish were turned upside down, flowing towards the sea like that. And they said, okay, where is this sediment coming from and so on? It comes way upstream, but you know, it was just killing all the fish in the water. So it has some, again, some impact, and all the carbon, again will be going through the fluvial system and marine system.
And they were killed not because it was polluted above, just because it was too much salty or something like that?
Too much sediment, so the fish cannot breathe with that. Okay, I don't have time to go through the whole, yeah, I'll start a little bit. I have 5 minutes maybe. Yeah, there's one thing that is very interesting, I find, with climate warming and science, and I just want you to be aware of that if you do conduct some experiment. We present the warming, you know, sometimes in steps, 0.5, 0. But in fact, it's absolutely not linear. We have interannual variability, and with climate warming, it's much higher. So we've heard about extremes, extreme heat extremes here in Europe, in Italy, everywhere. We have that in the Arctic as well. But then it's an extreme. What follows an extreme is something more average. So that will be warming extremes. I don't think we'll see cold extremes really. Anyway, not for now. And it's followed by normal years, which are necessarily a little bit colder than these extreme warm years. So, and another thing that has been modeled by global modelers is that the Arctic will be dominated by rain, so more rain than snow by the end of the century. And we start to see that. Summer precipitation early in the summer. Usually in the Arctic, it's in the fall. But we see it now in May, in June. In July, you start to have that, but it's totally new. And rain and filtration, what does it do to the permafrost? It's heat transfer. It's again convection, and it thaws the permafrost again 1 to 2 orders of magnitude faster than atmospheric warming. So these new rain events in the spring and early summer, they contribute to thaw faster the permafrost. So I want to give an example here from the summer 2019 in Nunavut. So we arrived for a totally different project. So this is Greenland, Baffin, Bidat Island, Arctic Cordillera. This is Bidat Island, and we work in this area here. So it's cold, -14, precipitation around 200 millimeters a year, and you have long and rigorous winters, so about 50, 100 degrees of freezing. So we arrived by helicopter, and we were flying around, and we saw many landslides. We call them active layer detachment. So this active layer that gets super saturated and then just flow down the slope. So this thing here is about 500-600 meters, if I remember well. And it's just a big mess of mud. So geomorphological student, they're not like physics student. What they like is when there's a catastrophe. They like to play in mud. They want a landslide. They want something collapse. And they're good at that. That's why I like to recruit physics students as well, because they will put numbers on these things. Geomorphological student will just dig. I want to see the ice. I want to see play in the mud. So you have here an example. So you have the permafrost, you have the active layer, and then you create a headscarp, and then it flows like that. What you need to have for that is the active layer that thaws rapidly. If it thaws slowly, it drains. You need high pore water pressure on the sediment. So you remember when we discussed that we have excess ice, we have more ice than the porosity can accumulate. So this water needs to go somewhere, and it has nowhere to go. So the pore water pressure goes up very, very fast if it thaws rapidly. And then eventually you reach the threshold and you have this landslide. So when and it's normal process, we see it here and there. But this very summer, we had a bunch of these landslides everywhere. And immediately, we arrive in June, immediately I said, this is not normal. Usually we will see that in the fall, August. We arrive in June and we have a lot of landslides. So, no, I'll skip this one. No, I'll take this one. What happened in this, we had a period of colder climate before 2019. 2019 was a warm summer. It started fast. You can see the increase. This is air temperature, and this is ground temperature. I have several met stations in this area, so I can extract the soil temperature. So you have 3 years of cooling, followed by a very quick warming. What happened with these 3 years of cooling in the active layer? Like we saw at the beginning of the course, the bottom of the active layer goes up. You create ice in this area. 3 years, only 3 years. And then we have this very warm summer. So what happened? You get into the ice you just formed, you release that water, you have extra pore water pressure, and then you trigger landslides. So it happens, but when you see it everywhere, something must have happened. So we looked at the precipitation nearby village, Pond Inlet, and on our station again. And the rain precipitation, you see very low, a little bit more. 2008 it starts, and then 2019 in July, we're already above all these years here. So we had a lot of rain, and it preconditioned for the thawing. So we have just no big rain events. So in May, almost nothing. In June it starts, but then in July, all this was really the infiltration of that water created a lot of heat transfer to the soil. And this is when we observe the active layer slides. So low temperature, aggradation of permafrost, transient layer, and formation of ice in this layer. Then we have the very warm summer, high temperature, melting, rainfall, rain infiltration, heat transfer, and then we have all the conditions to create the landslide. So this is a little bit the hypothetical framework for our stuff. So permafrost aggradation, thawing, extra thawing with water, and active layer detachment. Why I wanted to present it today? Because tomorrow I want to show you what we did in the lab. We modeled that in the lab. And we have these hypotheses. This is due to the presence of extra ice lenses, and this is due to the presence of water infiltration. So I'll show what we have done in the lab regarding that. And just to finish very quickly, impacts of ground subsidence on infrastructure. So this is a road in northern Quebec. So you should always contact the geomorphologist before building, especially if he has some civil engineering training. So this road was flat. Of course, we don't build roads like that. We're funny in Canada, but we don't build roads like that. So this was built over ice wedges. And then you change, and then we put asphalt. Big mistake. As a rule of thumb, no asphalt below the Arctic Circle, otherwise you completely degrade your permafrost. So we build, and we like black asphalt that rolls well and so on. You know, we're North American, sorry. And it degraded the ice wedge, then you're stuck with a road like that. And this is a famous, iconic Dawson Gold Rush period era where they built and they had no knowledge of permafrost, so it affects building. And who had that picture? You did. That picture was stolen by BBC, right? Was it? You found it on BBC, yeah. I have several pictures, field pictures that travels the internet, and they don't know. So you can have also on the roads formation of sinkholes, so very complicated for infrastructures. But, oh, this one I'll skip. But we also design mitigation measures to freeze back the permafrost, because where we have roads, and we use natural processes inspired by rock glaciers. Rock glaciers, you have cold air going into the interstice, the voids in the ground, and you form ice there. And then you have these rock glaciers flowing even into forests like that. So we mimic that, and we created a technique where we put big pipes in the road embankment, and we create natural convection by chimney effects. So you take the cold air in the winter, and it travels through, it follows the chimney effect if you want, and it cools the permafrost at its exit the embankment. So cold air getting in, traveling here, and warm air getting out. And with that, we're able to either control, stop permafrost degradation, or recreate permafrost. That's a really powerful feeling. Yeah, so let's, here, this is black air temperature. This is the inlet. As the air travels through the duct, it warms up, and then this is the outlet. So you can see the kind of pretty big 5°C temperature that travels through the road embankment. So that's a control section. That's a zero isotherm, pretty much like that. And then we just created, in just a matter of a winter, 1 meter aggradation of permafrost to control road degradation. Anyway, just a little application of natural principle and physics to road infrastructures inspired by nature. Thank you.